Hello everyone, my name is Jason and I'm going to be doing this presentation today on electrical and mechanical engineering. Part of the reason why we grouped these two together for this presentation is because the two of these disciplines tend to work hand in hand in the real world and with their final products that they design and put out. So just to go a little bit more into detail on what that means, on the left side, the electrical engineers, they create systems that process info and transmit energy. They study the applications of electricity, electronics, and electromagnetism. They plan and build computers, cell phones, radars, navigation systems, wiring and lighting in buildings, and cars and robots. Whereas on the right side, mechanical engineers, they use math and sciences to create moving objects. They study heat flow, fluid behavior, and motion, and they will design and create elevator, planes, air conditioning units, and cars and robots. These lists are not limited to exactly what's here. They do many more things than just this. But the reason cars and robots is bolded and colored is because for items that need both an electrical and a mechanical engineer to work on them for it to function, i.e. something that has a computer in it and something that has moving parts, because the moving parts will be by the mechanical engineer and the computer parts will be more by the electrical engineer. So two sides of the same coin. This is kind of just going deeper into that whole idea. The left side is stuff that's a little bit more specific to electrical engineering, and the stuff on the right is a little bit more specific to mechanical engineering. So if you were to look at this robot and guess which components were built by the electrical engineer and which were built by the mechanical engineer, what would you say was built by each one? Here's a hint. Take a look at the arrows and take a guess at which one. For the sake of this purpose, on the right side with the moving, waving arm, we're talking about the gears, the hinge in that elbow. That gear and the motion of it was probably designed by a mechanical engineer, whereas the left arrow pointing to his head, which is like the brain of the operations, it's what makes the arm move, but not why it moves, was designed by the electrical engineer, sending those electrical pulses out to tell the motors and the gears to spin. So part of why we are going to go into this is with the onset of this virus and the pandemic going around, the push for hands-free and contactless delivery systems are blowing up and becoming the normal now. So here's a short video. So part of why I put this video in here was for the action statement of is the future now, and the reason behind that statement is because innovation in anything that happens is driven by demand. So not many things are created that are not needed. And I think everybody would agree with me with saying something like this, Amazon delivering their packages with drone services, is something we could all see in the future. But with the pandemic around now, how soon is that future? Could we see it fast-tracked and potentially be sooner readily accessible for the general public? Like I said, the video is not real. This isn't real yet. It would be awesome if it could be in a shorter time frame, but not currently. So now, talking about drones a little bit more, again, going into more detail about the pandemic idea, they provide easy use, they provide easy transportation, they can go to remote locations. For instance, say if you had to video something, you can attach a video camera, and overall they're functional in society. So some drone movement. I'm going to go over this bottom section a little bit real quick. because it's the most important just for drone movement. So this one, looking at a front view, the copter's staying flat and the propellers are just spinning. This provides a thrust, which will bring it upwards. If we're looking at the rear view and say we wanted to turn right, the way this is functioning is it's leaning one way and it's going to be turning on a round angle. For pitch, the front of it's going to lean down and that's how it goes straight forward. And for yaw, this might be a little bit more of the complicated one. It's staying perfectly flat and it's rotating in place, instead of, say, like the roll image here where it's going to be going forward and turning. Yaw would just be turning in place. These 4 photos are just some examples of potential uses, if not already uses, where drones are used in the world today. The top right is more of a potential use with, say, a company like Walmart, Amazon, or large other distributors sending packages out to consumers. And the 2 on the left here with the water and the fire, they could be used in search and rescue or first response, depending on what can be attached to the drone to help save people in life risking events. The bottom right here, the drone is watering and or maybe putting pesticides or something, who knows, onto the crops here. But again, it's making an easier source rather than a bunch of people having to work into this field. It's just the one drone doing all the work. Touching upon some of the similarities with a drone and a plane, the forces are similar, but they're not identical. So for a plane to have flight, it needs to have lift, which this lift would be created from the wings, and in simple terms, the air pushing up on the wings to raise the plane. Gravity, which could be looked at as the overall weight. And for it to go forward, it's going to need to provide thrust, which will either be provided by the engines, and the drag is the resisting force from air particles, preventing the plane from going forward, slowing it down, I should say. Okay, and on this slide, I'm gonna go onto a website real quick, and I'm gonna show you some stuff that might be fun to play around with. So here, this is like an air, it's showing a wing and how air travels over a wing. So if you were to, say, model a plane or want to mess around with this, you can play around with the speed functions here, the altitude, and the wing area. Personally, I wouldn't touch the other ones as they make it a bit more complicated to understand. But say I wanted to change the speed here and I change it to 500, or if I change the altitude here to 35,000, 35. You will see these numbers in the top right, the lift value and the drag value, like I was talking about before in the presentation here. They will change. And if you just want to play around with it and see what stuff looks like, it's nothing too crazy. But back on this for a brief moment. When thinking about lift and, say, the weight and the thrust and the drag, for sustained flight, for it to be a plane, lift either needs to equal the weight or lift needs to be slightly larger than the weight, which would make it go up and rise, like a takeoff, let's say. And the following presentation, which will be an experiment on a paper airplane design with some alterations in the weight and whatnot, will be presented on our website by Kara, and I will link the website as well as some items for the experiment in the description below.